All right, here we go. 3, 2, 1. That was perfect. This is my third video on building a DIY version of the SpinLaunch concept. The full-size SpinLaunch is meant to throw rockets into space, and so far I've been able to replicate the release and launch of this system just on a small scale. However, I know I can make this cooler, so the obvious next step is to add rocket engines. I am sure nothing will go wrong. On top of this, I finally want to get video footage from onboard the rocket during a successful launch. This has been a goal of mine from the beginning of this project, and this video, we gotta make it happen. Before we get to any of that though, I want to make a couple improvements. If you haven't seen my previous videos, I'll link them below. But this system uses a giant spinning arm to basically throw a rocket upwards. There's a lot of debate online if this is even a good idea, but it's certainly fun to test. And what I noticed in my previous testing is this arm is pretty loud when it spins. This noise is caused by all the turbulence created by the arm spinning through the air. The tip of the arm is spinning at 80 miles an hour, so it's experiencing some pretty significant drag. I was curious if I could quantify this drag on the arm, so I talked to the guys over at Airshaper, which is a CFD tool that's very intuitive to use. They ran a simulation showing that this thing takes 400 watts of power just to overcome the air resistance at these speeds. And as you go faster, this will increase exponentially. To fix this turbulence problem, I designed some fairings in Onshape. To make these fairings, I just printed them out with one wall perimeter and very low infill to keep the weight down. For the leading edges, I wanted to keep some amount of strength, so I used some ABS filament that was filled with glass fibers. And despite being super lightweight and thin, these still feel very durable. Just for fun, I threw them onto the scale and I was pretty shocked that the leading edges only weighed 36 grams and the trailing edges only weighed 74. Now to be honest, the weight of these doesn't matter that much, but it keeps the already scary momentum of this arm from increasing anymore. And it uses less filament when they're lighter, so it's a win-win. A few bolts hold all these in place, and just looking at the cross-section you can see how much more aerodynamic it looks. Running another Airshaper simulation, we can see that with the fairings attached, the power required goes from 400 watts all the way down to 250 watts. That's almost a 40% reduction, which I was really happy with. On the end of the arm where the rocket is released, a small support arm gets added. This will be used for holding the igniter, and the igniters for these rockets are just little wire filaments covered in a burnable compound. Typically, alligator clips are used to connect the igniter to your launching device, but that's unreliable on a good day. So when this whole arm is spinning and everything's experiencing over 100 Gs, I don't think that's going to work. So I soldered XT30 connectors to the ignition wires and the igniter, which should make a reliable and easy to use connection. 3, 2, 1. Oh yeah. The power to ignite the rocket is supplied by the battery that's on board the arm, and all the timing is done by the electronics. A solid state switch called a FET is used to switch on and off the power to the igniter. These things are really small for how much power they can switch, so it was really easy to add onto the Breakout board. You may have noticed this Breakout board in a couple past projects, and this is actually a custom design I made a few months ago. I found that when I was using a normal proto board, I would end up with a bunch of wires connected to the 5 volt, the ground, the 3.3 volt pins, and it just got really annoying and messy. So I made these custom boards, and there's 2 different sizes, but both of them have the voltage lines and the ground lines broken out into a bunch of pads, which makes everything a lot cleaner. So far I've been really liking them, and I made them for the TT 4.0 and the Arduino Nano format boards. When you go to order PCBs, it's no extra work just to order a bunch of them. So I have a bunch of extra ones that I'll put a link in the description for where you can pick those up. Again, I've got a pretty limited number at the moment, but if people like them, maybe I'll order more. So far I've found them to be really handy, and I'd love your guys' feedback. With the upgrades to the SpinLaunch arm complete, the rockets themselves just need the motors. Luckily there's already a bunch of space free at the base of the rocket, so it was as simple as just printing some adapters to get the spacing right, and then doing some final balancing of the arm, and I think this thing's ready to go. So the next opportunity we had, we packed up the SpinLaunch into the truck again and headed out to test. The only free day I had happened to line up with like the coldest day on record of November. Oh my god, it's cold. So that made this whole process even harder. Last time we were here, it was like 90 degrees, and now, a month and a half later, it's 20 degrees. Ridiculous. Thanks, Ohio. Now we just gotta put the arm on there. And now, the new and improved arm. Dun da da da! Slide this guy on there. Boom. That thing looks crazy now. Despite the cold, setting this thing up in the field is not that hard. You really just have to put the arm on and tighten one bolt. I can't say that these upgrades to the arm are the most aesthetic thing I've ever made, but they should be functional, and that's what matters. I went ahead and plugged in the batteries, which is just 3 6S batteries in series, because the motor's meant to run on 72 volts. Let's do a double check here. Oh yeah. The rocket just gets attached to the end of the arm, and the reservoir can get filled with air. Now for this first test, the rocket does not have an engine in it. I just want to make sure the arm still works. Here we go. I think that's a good speed. 3, 2, 1. Woo-hoo-hoo! Listen, it was a little horizontal, but it went straight. We just gotta adjust the timing a little bit, and then we should be good to go. As you can see, the release of the rocket is super clean. However, the direction is just a little bit off. Luckily, this is easy enough to change by just modifying the software that's running on the arm. I mean, last video we did a lot with how fast can we get it to go. I still want to go faster, but I kind of want to just prove that you can actually light a rocket while it's spinning. So let's just put a rocket in there and send it. See what happens. So taking one of the rockets, I inserted the motor into the back of it. I think I made the press fit a little too tight, but at least it's not going to fall out now. And just like the previous rockets, it gets attached to the arm. And then for this one, an igniter gets inserted into the rocket motor. Now I'll be honest, it took a couple iterations to get the timing correct on this, and there were 2 launches that didn't go quite as planned. 3, 2, 1. However, by the 3rd attempt, I finally got it figured out. Just like that, we should be good to go. Moment of truth. All right, here we go. 3, 2, 1. That was incredible. I think we made the first SpinLaunch missile, not a rocket. Oh my God. That thing was just gonzo. That was awesome. I think it went 150 yards. That's like, I don't know, some number of meters. That's crazy. There it is. Thing came in like an absolute missile. Rocket is here. Launcher's all the way up there. That's wild. Still in good shape though. Now, although it did fly very straight and the rocket ignited perfectly, the goal of this is not to design a spin-launch missile. So let's see if we can actually launch this thing straight up. All right, here we go. 3, 2, 1. Woo! Heads up. That was perfect. Dog got excited. Turns out my dog's a big fan of SpinLaunch as well, because she was very excited about this nearly perfect launch. I mean, I honestly couldn't ask for much better. The rocket released at the perfect time, and the engine was already lit. And this thing definitely went higher than all my previous attempts with this SpinLaunch arm. Look at that. The thing went into the ground. That was the best one today. Can we just talk about how well that works for a second? Oh my God. Everything just went perfect. That never happens. All right, that last launch was almost perfect. The only thing wrong was I didn't have the camera on board. So I put my little Insta360 camera in there, and hopefully this one goes straight up as well. I'm gonna try to do everything the same speed. This is the same rocket motor, same rocket even. So hopefully we get the same result. Here we go. Spinning it back up. All right, here we go. 3, 2, 1. Woo! Look at that. That was perfect. Ooh. That was a pretty hard hit. Hopefully the camera survived that. As you can see in the slow-mo, this was another nearly perfect launch, and the rocket motor lit flawlessly. And finally, we also got some awesome onboard footage. This onboard footage turned out awesome, and this rocket set a new record for my SpinLaunch system at 350 feet in altitude, which is not bad. Wow, another great launch. Dude, can we just talk about how perfect all these ignitions are? I was really trying to keep all the electronics off of the rocket, so I'm very happy that I was able to ignite it before you let go. That way all the electronics can stay on the arm itself and not have to put onboard computers and sensors onto the actual rocket. Keeps things way simpler. All right, let's go get the camera. Oh, look at this. First off, still recording. It's still recording, and look how close the camera was to just getting driven into the ground. Thing is so close. Woo! All right, well, this thing works surprisingly well. We put rocket motors in the rockets now, and they actually lit perfectly every time. And we got 2 really, really good releases, as well as one horizontal missile style release, which is pretty cool. At this point, I've gotten further with this project than I initially expected. And what made it all possible was a ton of design iterations. And that's where the sponsor of this video, Onshape, comes in. Onshape is an entirely cloud-native CAD platform, which I've been using for multiple years now. It has all the features needed to make complex designs and assemblies like this, and it streamlines the whole process without needing clunky files or things like that. And what's really cool is they have very robust version control. You can even fork things just like on GitHub. On this SpinLaunch project, I used this version control to keep my old designs, but make improvements like the aerodynamic fairings and the variable release timing. Onshape is completely parametric, so you can go back in your design and change features, and everything else just updates around it. This saves a ton of time. They also have some really cool stress analysis tools, as well as an entire cam studio, and this is all just built into the platform. Onshape is free to use, and honestly, I can't recommend it enough. So check it out using the link in the description below, and use it for your next project. But overall, this project has been amazing. Everything works so much better than I expected, and I don't know if it gives me any hope for the real SpinLaunch concept, but it's been at least fun tinkering with it. If you guys have any other ideas on what you want me to do with this or a different project, just let me know, and subscribe for more. There'll be more projects coming soon, so I'll see you there.